Dear students, in the last lecture, we have finished limit and continuity of complex function. Now, let us begin our next topic. Your next topic is what? Differentiability of a complex function. Differentiability. Differentiability. Differentiability of a function. Differentiability of a function. Here we are talking about complex function, not in general function. Okay. So how to define differentiability of a function? So definition of function, a function f of z, f of z, which is defined, which is defined in the domain, in the domain D, is said to be differentiable, said to be differentiable, differentiable at at the point z equal to z naught if limit z tending to z naught f of z minus f of z naught divided by z minus z naught exists and and which is equal to, which is equal to f dash of z naught. What is your definition of differentiability of a function? A function f of z, which is defined in the given domain D, is said to be differentiable at given point z equal to z naught if this condition hold. Limit z tending to z naught f of z minus f of z naught and divide by z minus z naught, and this limit must be exist and which is equal to the f dash of z naught. Then we can say that that function is differentiable at the given point z equal to z naught. Okay. And if function is differentiable at z equal to z naught, then we can say that the function is differentiable in the given domain D. Okay. Now here we write down here some note, and what is that? If f of z is differentiable at a point z equal to what? Z naught, then we can say that then f of z is differentiable differentiable on the domain D, on the domain D. Means what? If the given function is differentiable each and every point of the domain D, then we can say that function is differentiable on the domain D. Getting? So this is the simple definition for differentiability of a function. Getting? Okay. Now let us do some example based on this, then we can understand what is the differentiability of the function. So example, and what is the example? Let f of z equal to what? Equal to mod of z be a given function, be a given function. Okay, given function, and so that f of z is not differentiable, z is not differentiable at z equal to what? Z equal to 0. Okay, let us see how to show this function is not differentiable at the origin. Getting? So solution, or you can say the proof of this problem. And what is given to you? Given that function f of z, and which is equal to what? Modulus of z. Okay. Now, what is the definition of our differentiability of a function? Since we know that, since we know that, what is that? F dash of z naught, and which is equal to what? Which is equal to limit z tending to z naught f of z minus f of z naught, and divide by what? Z minus z naught. Okay, but here z naught is what? Your z naught is 0. Okay, so therefore f dash of 0, which is equal to limit z.
सर z इक्वल टू 0 है ना.
Here, what is your definition at z equal to z naught? But z naught is what? Z naught is 0, no? 0, no? By comparing this two, so you'll get what? Z naught is 0. Getting? So limit z tending to 0 f of z as it is. This is f of z minus f of 0, f of 0, and divide by what? Divide by z minus 0. Okay, so this equal to what? Limit z tending to 0. F of z is what? Your f of z is mod z. This is mod z minus f of 0. So put z equal to 0 in this function, so you'll get what? F of 0 equal to modulus of 0. Okay, modulus of 0, and this is divided by z. Okay, this is divided by z. Okay, so now let us move to the next page, then simplify this or solve this. So next page, so therefore we write f dash of 0, and which is equal to what? Limit z tending to 0, and here you will have modulus of z divided by z only, because here modulus of 0 is 0. Okay, now let us find the limit of this. Before finding limit of this, we must know the condition of but the definition of modulus. Okay, and what is the definition of modulus? But modulus of z is defined like this. This equal to what? Z if z is what? Greater than equal to 0, and this is also equal to minus of z if z is what? Less than 0. So this function this function means what? Modulus of z is split into two function. Okay, so we will check the limit for each function. So therefore f dash of 0, and which is equal to what? Limit z tending to what? 0 plus. Okay, we taking here a right hand limit. Okay, so instead of z we put, instead of modulus of z we will put here z. So we will have z divided by z, but this z and this z cancel. You will have limit what? You will have limit 1. Getting? Now also, so this is what? F dash of 0, and this equal to limit z minus sorry, z tending to 0 minus. Okay, z tending to 0 minus. So instead of modulus of z, we putting over minus z. So this is minus z divided by z, and this z cancel. You will have minus 1. Okay, you will have minus 1. Okay, therefore we can say that limit of the function is not unique. If your limit exists, so it must be unique. Otherwise, you can say that limit does not exist. So here you can write, since limit of the function is not unique, since limit of the function f of z as z tending to 0 is is you can say is not unique. Okay, is not unique. Therefore, you can say that f dash of 0 f dash of 0 does not exist. Okay, does not exist. Therefore, f of z is not differentiable, is not differentiable differentiable at z equal to 0. Why this so? Because limit of the function does not exist. So if limit does not exist, then function is not differentiable at the given point. Hence we can say that function is not differentiable in the domain also. Okay, should I move to the next problem?
Yes, sir.
Okay, now let us do the another problem. Example. uh, so that so that f of z equal to sine z is a differentiable function, is a differentiable function at the origin, at the origin. What I have to do over here? We have to show that the function f of z is differentiable at the origin. Origin means what? The function must be differentiable at the point z equal to 0. Okay. Now proof of this function. Proof. Let us see how to show the function is differentiable at the origin. So first we write down, let function f of z is equal to what? Is equal to sine z. Okay, this function is given to you, and what I have to do? Have to show that the function is differentiable at the origin. So to show that f of z is differentiable, f of z is differentiable at the point z equal to what? 0. Okay, but we know that differentiability at the origin have the definition, that is what? Since we know that since we know that f dash of 0, and this is equal to what? This is equal to limit z tending to 0 f of z minus f of 0, and this divide by what? Z minus 0. Getting? So this is your definition of differentiability of a function. So therefore we will have f dash of 0. Okay, f dash of 0, and this is equal to what? Limit z tending to 0. Okay, but f of z is what? F of z is what? Sine z. F of z is sine z minus f of 0. f of 0 is what? Sine 0, and divide by what? Z minus 0. And this can be written as what? Limit z tending to 0 and sine z, but sine 0 is what? Sine 0 is 0, okay? And divide by what? Only z. And this can be written as what? Limit z tending to 0 sine z by z. But we know that what? Limit x tending to 0 sine x upon x is what? 1. So this is equal to what? This is equal to 1. Okay. Okay. Now from this you can conclude that therefore f of z equal to what? Sine z is differentiable differentiable at at z equal to 0. Okay. Therefore f of z can be differentiable f of z can be differentiable as usual manner. F of z can be differentiable as usual manner. Okay. Usual manner means what? Like lower class, we are differentiating function sine, cos, exponential function, logarithmic function as a general function. Okay. So f of z can be differentiable as a linear manner. Hence f dash of z equal to what? Cos z. Okay. F dash of z is cos z. So this implies that f dash of 0 is what? 1. Getting? Hence proved. Hence proved. Okay. I hope you understood this problem. Yes or no, student? You got it?
Yes, sir.
Yeah, sir.
Okay. Should I give exercise problem for you? Let us move to the next page. Then we'll have some exercise problem. Mm, example. Example. So that the function. So that the function f of z equal to what? F of z equal to cos z is differentiable at z equal to I. Okay, z equal to I. So, and the next problem is what? Example. Should I do this problem right now, or should I give exercise for you? So that the function f of z, which is equal to what? Modulus of z square, is continuous. Is continuous. Is continuous, but nowhere differentiable. Nowhere differentiable. Differentiable except except at the origin. At the origin. Okay. So these two problem is homework for you. So please do this problem at your home. So here, how to show or how to solve this problem. First one is what? Function is given to you, that is f of z equal to cos z, and we have to show that this function is differentiable at the point z equal to I. So for this, what I have to do, just write down the definition of differentiability of the function f of z at z equal to I. Here you will take limit at z tending to I. Okay, f of z minus f of I divide by what? Z minus I. Okay, now the numerator become what? Cos z minus cos I. Here you have to apply the formula for cos c minus cos d. Okay, then simplify them and apply the limit, and you will get the required result. Okay, and you will able to show the function is differentiable at the point z equal to I. Getting? So this is for first case, first problem. Now you have to solve the second one and see how to solve the second one in similar way like very first problem we have seen. So what I have to do first? You first have to show the function is continuous. Okay, continuous at the origin. You know how to prove the function is continuous in the last lecture. Okay, so by using last lecture, you just prove the function is continuous at the origin. Okay, so this is for first step. Now the second step is what? The second step is what? You have to show the function is differentiable only at the origin and nowhere it is differentiable. Okay, and you have to show that what? By definition of differentiability of the function as f dash of 0 equal to what? Limit z tending to 0 f of z minus f of 0 divided by z minus 0. Okay, and you apply the definition of mod z over there and show that the function is differentiable only at the origin and it is not differentiable anywhere except the point origin. Getting? So in this way you can solve these two problem. I hope you understood how to solve this problem. Okay, now let us move to the next topic, that is what? Analytic of a function, which is very important topic for you. Analytic of a function. So before that we have seen that what is the differentiability of the function. Now we will continue for the topic, that is what? Analytic of function. Analytic of a function. Analytic of function. See here, what is the analytic of function? Let us see the definition. A function f of z is said to be analytic, is said to be analytic, said to be analytic, or you can say regular, said to be regular, or there is another name, holomorphic. Holomorphic. Okay, a function f of z is said to be analytic or regular or holomorphic. Okay, so these are the name of the function analytic. Okay, is said to be analytic at the point at the point at z equal to z naught in the given domain, in the given domain D, given domain D, if it is differentiable at each and every point every point in the neighborhood of z. So what is the definition of analytic function? A function f of z is said to be analytic, or you can say regular, or you can say holomorphic. Holomorphic at the point z equal to z naught. Holomorphic at the point z equal to z naught in the given domain D if the function differentiable at each and every point in the never neighborhood. Okay. Ne- uh, it is differentiable at each and every point in the neighborhood of z. Neighborhood of z means what? Suppose this is your domain, this is your whole domain. Okay. So what is the analytic of a function? A function is said to be analytic if analytic at the point z equal to z naught. Okay. In the given domain D. This is your z equal to z naught. Okay. So we can say that the function is analytic in the domain D if the function is what differentiable at this point. So what is the analytic of function? Function is said to be analytic at the point z equal to z naught in the given domain D if it is differentiable and each and every point in the neighborhood of z in the in the domain. Okay, so this is your definition of analytic function. Now let us do some problem based on this, and before that we must state Cauchy-Riemann equation in Cartesian coordinate. Okay, then we will state Cauchy-Riemann equation in Cartesian coordinate. Cauchy-Riemann Cauchy-Riemann equation Cauchy-Riemann equation in Cartesian coordinate. Cartesian coordinate. Cartesian coordinate. Okay. And what is the Cauchy-Riemann equation in Cartesian coordinate? Cauchy-Riemann equation is also known as what? CR equation. C dash R equation. Okay. So there are necessary and sufficient condition for a function is to be analytic is known as what? Cauchy-Riemann equation. So we will have theorem, or you can say the result. Theorem. The necessary and sufficient condition. The necessary and sufficient condition. Sufficient conditions. Necessary and sufficient conditions for a single value continuous function. For a single valued continuous function. Continuous function f of z equal to what? U of x comma y plus I v of x comma y to be analytic, to be analytic in the domain in the domain D, in the domain D, or you can say region, both are same. In the domain D are first case all partial derivative dou u by dou x comma dou u by dou y comma dou v by dou x and dou v by dou I are are continuous continuous functions of continuous functions of x and y, continuous functions of x and y in the domain D, in the domain D. And the second condition is what? And the second condition, it must satisfy the equation, that is what? Dou u by dou x equal to dou v by dou y and and dou u by dou y, and which is equal to minus dou v by dou x. Okay, dou v by dou x. uh, you can also state that, you can also write that is in another form, that is ux equal to what? Vy and uy equal to what? Minus vx. Okay, at each point of D. Okay, and condition 2 is known as what? The condition 2 is known as condition, the condition 2 is known as Cauchy-Riemann equation. Cauchy-Riemann equation. Okay, and this is also known as what? That CR equation. That is CR equation. CR equations. Okay, so this is the necessary and sufficient condition for a function is to be analytic in the given region D. Okay, so what is the necessary and sufficient condition for a function to be analytic? The first condition is what? All partial derivative dou u by dou x, dou v by dou y, and dou v by dou x and dou v by dou y are must be continuous. Okay, must be continuous in the given domain D. So our partial derivatives are what? Functions of x and y. Okay, and which must be continuous at the given domain D. And the second condition is what? The second condition is it function f must satisfy, function f must satisfy the CR equation. Means what? Dou u by dou x equal to dou v by dou y and dou u by dou y equal to what? Negative or dou v by dou x. So these are two conditions, and your function must satisfy these two conditions. So we can say that the function is what? Analytic. Okay, so these are the necessary and sufficient condition for a function is to be analytic. Got it? Others?
Yes, sir. Yes.
Chaliye, let us do some problem based on this, then you will understand what is the Cauchy-Riemann
Sir.
equation. So
So,
before, yes, before doing problem, we must note that, we first note, important note, the Cauchy-Riemann equation are the Cauchy-Riemann Cauchy-Riemann equations are only necessary condition, only necessary conditions, for a function is to be analytic. for a function is to be analytic, okay, but it is not sufficient, but it is not sufficient, okay. Means what? If your function satisfy the CR equation, so it is not guaranteed that your function is analytic. Getting? तो CR equation only क्या है? This is only sufficient necessary condition, but it is not sufficient. Okay. चलिए. Let us move to the example. So there is some problem which satisfy the CR equation, but it is not an analytic function. Okay. You will find some example later. Example. So that f of z equal to e raised to z is analytic. So that this function is what? Analytic function. Okay. Uh, Solution. Okay. So what is given to you? Just write down. Given f of z equal to what? E raised to z is given to you. Okay. So but we know that z is what? Ex plus iy. Z is x plus iy. Okay. So therefore f of f of f of what? Ex plus iy, and this is equal to what? E raised to x plus iy. Okay. So this can also be written as what? F of x comma y, and which is equal to what? F of z. Okay. And this is equal to e raised to x into e raised to I y. Okay. So therefore we can write here f of z equal to what? F of z equal to e raised to x, and e raised to I y can be written as what? Cos y plus I sin y. Okay. Cos y plus I sin y. Since what? E raised to I theta can be written as what? Cos theta plus I sin theta. This is the result. Okay. You remember this. So now just multiply this inside. So this become e raised to x cos y and plus e raised to x I e raised to x sin y. Okay. Now comparing comparing this with f of z equal to what?
U
U
plus
ex comma
IV.
y, yes, plus I b of ex comma y. Okay. We get u of x comma y. U is what? Function of x comma y. That is what? U of x comma y is first term, real part. That is e raised to x cos y, and b of x is what? X comma y, and this is equal to what? This is equal to e raised to x sin
Sin Y.
y. Okay. I and I both are equal, so no need to write here. Okay. So this is the real part and this is your imaginary part. Okay. Now differentiate u with respect to x. So differentiating u partially with respect to x. So dou u by dou x, and this equal to, if we are differentiating with respect to x, so y will be constant. So okay. So this become what? E raised to x only and cos y as it is. Okay. Now differentiating u again with respect to y. Differentiating u again with respect to y. So dou u by dou y, and this is equal to what? In this case, e raised to x is constant. So e raised to x, what is the
Sin
derivative of
Y.
cos? Minus. Derivative of cos is what? Minus sine. So this is sine y. Okay. Now Now you differentiate this v partially with respect to x. So dou v by dou x, and this is equal to what? E raised to x. We differentiating with respect to x, so y will be constant, and e raised to x sine y. Derivative of e raised to x is same as e raised to x. Now differentiating v partially with respect to y. So in this case, e raised to x is constant. So e raised to x as it is, and
cos
derivative of
y.
sine is what? Cos y. Okay. Now, what is the CR equation? Therefore,
CR equation.
yes, therefore, just listen. Therefore, dou u by dou x, and which is equal to what? E raised to
So
x, e raised to x cos y. Okay. But this equal to what? E raised to x cos y is what?
dou v
Dou
by
v.
dou x.
Yes. Dou v by dou y. Okay. Also dou dou u by dou y. Dou u by dou y is what? Minus e raised to x sine y. But what? E raised to x sine y is what? V of
Minus of
x.
2.
Yes.
Minus
V of what? Dou v by dou x. Okay. Therefore, we can say that from 1 and 2, from 1 and 2, from 1 and 2, we can say that from 1 and 2, we can say that dou u by dou x, and which is equal to what? Dou v by dou y, and dou u by dou y equal to negative of dou v by dou x. Okay. And also, let us move to the next page. Also, all partial derivatives all partial derivatives, that is what? Dou u by dou x, comma dou u by dou y, comma dou v by dou x, and dou v by dou y are continuous. Okay. Therefore, by necessary and sufficient condition for a function, therefore by necessary and sufficient conditions condition conditions, we can say that by necessary and sufficient conditions of of analytic function, we can say that f of z is what? F of z equal to e raised to z is analytic. Analytic. Okay. Hence
analytic
proved.
function.
Yes, analytic function. You can write analytic function. Okay. Hence proved. Okay. So this is the simple proof of the function is to be analytic. I hope you understood how to prove this function is to be analytic. Okay.
सर लास्ट वाला पेज वापस दिखाइए.
Last wala. Uh, okay. Now should I give some exercise? Let us write down the exercise. Example. Prove that the following functions are analytic. Following functions are analytic. Okay, so that the following functions are analytic. Number one, write down cos z Number 2, you have to take hyperbolic function sine 2z, and number 3, you can take hyperbolic cos 3z and so on. Okay, similarly you can show all these things. Functions are analytic function. So here what I have to do, just replace z by x plus iy. Okay, and apply the formula of, so if you replacing here, just see here, first problem, this is cos z. Okay, so just replace here cos ex plus iy. Okay, now here you apply the formula for cos a plus b. Okay, then equate this function as a real and imaginary part. Okay, so you will get u equal to real part and b equal to imaginary part, and differentiate them partially with respect to x and y, and again differentiate v partially with respect to x and y, and check whether the function is whether the CR equation satisfy or not. If so, you are able to show the function is what, analytic. Getting? So इस तरह से आपको solve करना है. Okay, so this is exercise for you, so please do this problem at your home.
टाइम खत्म.
Okay, thank you all of you for joining to us, and we will meet on tomorrow. Thank you.